Welcome to Fox Lecture 27, and today we're going totally wild. Okay, we're starting on the board because we're going to talk about what can and what cannot be computed. Okay. And today's lecture is not going to have a punchline. Today's lecture is the punchline for the whole course. Okay. And so, Orange Malik is here, and you know what Orange Malik means. Important stuff. Okay, quick recap because it's important. So I have here, last time we were talking about Turing machines, and so what I have here is an example of a Turing machine. One way to sort of visualize it, you have your CPU, your DFA, which has a read-write head, and it can move around left and right. Okay? And here I'm showing an input string, which we typically call W, and there's the beacon symbol, which is kind of like base, to which the DFA can return whenever it needs to. Okay, and so when you have a Turing machine, it's described by, its states, the symbols that can be seen on the tape, and also what are its instructions. So what does it do depending on its state and what it reads. Okay. And that entire Turing machine can be described by its encoding into a finite binary string. So this is important. Every Turing machine is effectively a finite binary string. Okay. Now, how does the Turing machine operate? So, it starts at its beacon symbol, it moves around processing the input, okay, and eventually it will either halt and say yes, okay, it will either halt and say no, or this ability to move around has introduced a sort of a thorn in our thigh. It could infinite loop, and we saw an example of a very simple Turing machine that infinite loops last time, okay. And so if the Turing machine, on some inputs might go into an infinite loop, we call this a recognizer. And we've all written programs that have occasionally gone into infinite loops and we didn't know what the hell was going on, and so we went and had lunch. Okay. Now, this is bad. Okay. We can't use, computing machines that could go on forever in practice, because then we can't even distinguish between the situation where it's going to halt and say yes after a very long time versus is it infinite looping. We would never know. Okay. We would not. So even the situations where it does halt and say yes become useless to us, especially if those take a long time. We start suspecting, have I gone into an infinite loop? So these recognizers, although in theory can exist and are useful to analyze in theory, we're not interested in recognizers in practice. Okay, so a Turing machine that would be useful in practice is one which always halts. So a computer program, think computer program because that's where we're going. A computer program, a Turing machine that always halts and either says yes or no. And if a Turing machine on every input always halts, okay, then we call it a decider. Okay. Now, let's say you have a decider, okay, and we'll call it M, and we define the language that is decided by M as the strings on which M halts and says yes. That definition also works for recognizers, okay? So the language is the set of strings on which your Turing machine halts and says yes. Okay, and if M is a decider, then the language that corresponds to this decider on which it halts and says yes is called a decidable language. Okay, and essentially the Church-Turing thesis, okay, is the claim, the thesis that, whatever we think of as an intuitive notion of an algorithm, okay, is a Turing machine decider. So the concept of a Turing machine that always halts is capturing our entire intuitive notion of what is an algorithm. Okay. And when we talk algorithm, we are not interested in things that go on forever. So that makes sense that we are only interested in deciders. Okay. And what it means to have an algorithm to solve a problem is exactly the claim that you have a Turing machine that can solve a problem. So anything you can do with an algorithm, you can do with a Turing machine, and that has withstood the test of time. That thesis has not yet been disproven. Okay. And so what it means for a problem to be solvable is that, so remember what a problem is. It's a set of binary strings. It means that problem is a decidable language. So there is some Turing machine decider whose set of strings on which it halts with a yes is exactly the problem that you are interested in. Then that problem becomes solvable. And for all other strings, because it's a decider, it must halt and say no. So a Turing machine decider is very special. Either halts and says yes or halts and says no. Cannot go into an infinite loop, and for obvious practical reasons. Okay, so now we're going to come back and we're going to talk about solvable and unsolvable problems, and we need to get a few more concepts going. Okay, so let's consider a simple problem. Okay, so let's consider the problem L, which is Okay, so now, last time we talked about any object you want, you can encode into a string. So let's talk about graphs, which are encoded as strings. Okay, so we use this notation with the angle brackets to indicate, so you have a graph and it's encoded as a string. So I'm interested in the graph strings, the strings that represent graphs, which are connected. G is connected. Okay, so let's do an example of such a graph. Okay, so here's its encoding. Okay, its encoding is going to start with the nodes. So let's say 2, 1, 3, 4. Okay, so I have nodes and then I have edges. So I'll put a punctuation, let's say, and I have the edge 1, 2. Okay, I have the edge 1, 2. I have the edge 2, 3, and the edge 1, 3. 2, 3, and 1, 3. Okay, and I also have the edge 3, 4. So let's draw this graph. So I have vertices 2, 1, 3, let's say 4. I have the edge 1, 2. I have the edge 2, 3. Okay, I have the edge 1, 3. And I have the edge 3, 4. Okay, so there, just to show you that I have a graph, I encoded it as a string, and the language is consisting of all such strings for which the graph is connected. So this string would be in this language, in this computing problem, because it is connected. Now let's build a Turing machine to solve this problem, and we don't want to even go into the level of pseudocode which says how a Turing machine moves back and forth. So I'm going to now illustrate to you the most common way in which we describe Turing machines, which is what I call a Turing machine sketch. So a Turing machine sketch to solve this problem. Okay. And so this is a very high level description of the solution. And this is what we today would typically call pseudocode. Okay. So I'm calling it a Turing machine sketch. So step 1. Okay. Well, check the format. Make sure that the string that has been input is a valid graph. Check input string is a valid graph. Okay. Step 2. Okay. Now, if I were showing you all the details, I will tell you how the actual head moves back and forth in order to implement my steps. But now I'm going very, very high level, sort of 30,000 feet description of the Turing machine. So, what's the general idea? To check if this graph is connected. What I'm going to do is I'm going to start at some vertex. So I'm going to mark the first vertex. Mark first vertex. And then I'm going to repeat the following algorithm. For every marked vertex, find an edge going out of one of those marked vertices, okay, to an unmarked vertex, okay, and mark that unmarked vertex. So, repeat. For, find an edge from a marked vertex to an unmarked vertex. So let's call the marked vertex, let's call it, let's say A, and let's call the unmarked vertex B, okay, and mark B. Okay, so let's see. Repeat. Find an edge from a marked vertex. So I'm just going to start by marking the first vertex. So the first vertex is 2, so I mark the first vertex. Okay, now repeat. Find an edge from a marked vertex, so 2, to an unmarked vertex, for example, to 3. Okay, mark the unmarked vertex. Okay. Now find an edge from a marked vertex, so a marked vertex could be either 2 or 3, to an unmarked vertex. So let's say I find the edge from 2 to 1. So I find the edge from 2 to 1, and now I mark the unmarked vertex. Okay, repeat. Find an edge from a marked vertex to an unmarked vertex. So a marked vertex to an unmarked vertex. Well, there's now only one such edge from 3 to 4. Mark the unmarked vertex. Find an edge from a marked vertex to an unmarked vertex. Oh, there are no more. Okay, so my end of the algorithm is when there are no such edges. Okay, that means you now check if all vertices are marked. Check if all vertices are marked. If so, you say yes. If not, you say no. Okay. So in this example, we now check all vertices are marked. We say yes. Let's do an example where, all vertices may not get marked. So let's consider 2, 1, 3, like this. Okay. And I have 4, but I don't have the edge 3, 4. So that corresponds to this string. Okay. So now it's this graph. So I run this algorithm. I mark the first vertex. Okay, so I mark the first vertex. Then I find an edge to from a marked vertex to an unmarked vertex. For example, this edge, I mark it. I find an edge from a marked vertex to an unmarked vertex. I mark it. Okay, there are no more edges from a marked vertex to an unmarked vertex. And so I come to step 3. I check, are all my vertices marked? No. And so I say no, not connected. Okay. So this algorithm solves the problem. Now we're not going to prove that it solves the problem, but you can convince yourself that it solves the problem. It determines correctly whether a graph is connected or not. Okay, but the point that I want to make is that even though this is at a very high level, we could sort of see how now the Turing machine would move around to do each of these steps. So if you could flesh it out as individual steps that correspond to these primitives of read, decide what to do, write, and then move. Okay, and change states. Okay, so you could think of I'm in the state where I'm marking. When I can no longer mark, I'm in the state where I'm checking. So I will systematically, I'll start by marking this guy, then I'll go here and look for edges that involve marked vertices and something that's unmarked. So for each edge that I come to, I have to go back and see, is it an edge between a marked and an unmarked? If yes, boom, I can mark the other part of the edge, and so on, I keep going. Okay? So this is how we will typically be formulating Turing machine algorithms from now on. And now you can see that because this can be implemented using these primitive moves, okay, this Church-Turing hypothesis starts becoming plausible now. So this is an algorithm, what we would call an algorithm, and look, we can implement it as a Turing machine. So whatever you think of as an algorithm is a Turing machine, and if it must always halt, it's a decider. Okay.